Hi everyone, and welcome to today's Daily Booster. First thing before we jump into any of our topics is our formula for today. And today's daily formula is work done. So work done in joules is force in newtons times the distance in meters. Just go careful with this one to look out in the question, because sometimes what they'll do is they'll give you a distance in centimeters, not meters. So make sure you convert to meters first. For today's Biology Blast, we're going to be having a look at a couple of aspects from B6, that final biology topic, all about health and disease. Before we can really dive into this, we need to know three key terms: health, fitness, and disease. When we are talking about someone and health, this means they are free from disease. So if someone is healthy, they are free from disease. If we're talking about someone's fitness, this is their ability to carry out an activity. And then if we're referring to a disease in general, then that is a condition caused by any part of the body not functioning properly. So do go careful on health and fitness. They are not the same phrase at all. Health, free from disease; fitness, ability to carry out an activity. Where we talk about disease, we've got two categories we'll split them into: communicable, the ones that spread from one person to another, and non-communicable diseases, those that do not spread from one person to another. The second bit we're going to focus on is all linked into those communicable diseases, the ones that can spread from one person to another. And one of the techniques we can use to reduce that spread. And the technique we're going to look at is vaccination. When we look at vaccines, what we're referring to is usually an injection that you are going to have that's going to then kickstart your immune system and therefore make you immune to that particular pathogen. So, how does it work? The vaccine itself will contain a small amount of dead, or this thing attenuated, which just means weakened, pathogens. So within the vaccine, what we've got is a small amount of the dead pathogen or some weakened or attenuated pathogens. So what we then do is we'll put that into a nice syringe, and it will then be injected into the body. Once that happens, we've got this special type of white blood cell called lymphocytes, and the lymphocytes will produce antibodies to the pathogen. The key thing about these antibodies is they are complementary in shape to the antigen. So if you look at the little picture on the right here, we can see we've got our white blood cell, the lymphocyte. On the surface, they've got these little structures called antibodies, they're proteins. And the shape of that antibody is complementary to the antigen. Now, the antigen is a protein that is specific to the pathogen. So pathogens have antigens that have a very specific shape, and then our lymphocytes make antibodies that are complementary to that antigen. Once that actually happens, we've actually got these lymphocytes that are capable of making those antibodies. And the antibodies are obviously specific to one particular antigen. Once we fought off that particular infection, in this case from a vaccine, then what happens is our body will keep these lymphocytes in the form of memory cells. Now, the memory cells are the ones that remain in the body. You don't keep vast quantities of lymphocytes producing antibodies for every pathogen you've ever encountered. That would be really wasteful of our resources. So instead, we have some memory cells that remain in the body. That means that if we then encounter the same pathogen in the future, the memory cells are able to replicate quickly and make antibodies before the pathogen can cause symptoms in you. That's what we mean by immunity. It's not preventing the pathogen from getting into you, it's just fighting off that infection before it really has a chance to take hold. And the reason it does that is because we exposed your immune system, those white blood cells, to some of the pathogen with the vaccine. Remember, we inserted some dead or inactive pathogen right at the beginning. The antigen was there, our body recognised it and made those memory cells for us. And that's how vaccination works. Quick reminder of today's daily formula. Work done in joules is the force in newtons times the distance in meters. Today's chemistry check comes from C5, so the 5th chemistry topic, which will occur on obviously the 2nd chemistry paper. And we're going to look at equilibrium position. So this is something that occurs in reversible reactions. And hopefully we remember we have a reversible reaction where we see this arrow. Now, basically the equilibrium position is a description of the relative amounts of reactants and products in our reaction mixture when they are at equilibrium. So we will either describe it as being on the left or on the right. So we describe it as the equilibrium position being on the left or the equilibrium position is on the right. If we're saying the equilibrium position is on the left, then what we're saying is the concentration of reactants is greater than the concentration of products. If, however, we say the equilibrium position is on the right, that means the concentration of reactants is less than the concentration of products. And one of the key things, and one of the topics they like to ask you about a lot, is all to do with how changing the conditions that a reaction takes place in will alter the equilibrium position. So let's look at those conditions one at a time to explain what the effect is and why. So the first condition is pressure. If we're going for a description, so if they say describe the effect of increasing pressure on the equilibrium position, then we would need to write down this bit. So if you increase the pressure, then it's going to move in the direction of the fewest moles of gas. So that would be where our description comes in. It would move to the left or the right, depending on where the fewer moles of gas were. Usually it's going to be an explain question though. So you would have to start off by saying, if you increase the pressure, the equilibrium position moves in the direction of the fewest moles of gas, and then obviously explain which way that is. So let's look at our example here. We've got a balance symbol equation in the middle here. So we've got 2 moles of sulfur dioxide, which is a gas we know from the state symbol here. We have 1 mole of oxygen gas, and then on the right we've got 2 moles of sulfur trioxide gas. If we look first of all, we have 2 moles of sulfur dioxide, 1 mole of oxygen, so that means we've got 3 moles of gas on the left. On the right we've got 2 moles because we've only got sulfur trioxide and there's 2 moles of it. So we can work out number of moles on each side to start. Because we've got 3 moles of gas on the left and 2 on the right, if we increase the pressure, it moves to the right. So our equilibrium position is going to move in the direction of the fewest moles of gas. We only have 2 on the right, so it moves to the right. If we decrease the pressure, the opposite's true. It's going to move to the left. So we can see there how changing the pressure, we can alter the amount of product we make. Condition number 2 is concentration. If we increase the concentration of a substance, then the equilibrium position moves in the direction away from the substance we increase the concentration of. So we've got a balance symbol equation there, and then if we're increasing the concentration of hydrochloric acid, there's hydrochloric acid, so we increase the concentration of that, then equilibrium position moves to the right because it moves away from the substance we increase the concentration of. Condition number 3 is temperature. So if we increase the temperature, then what happens to the equilibrium position? It moves in the direction of the endothermic change. If they're going to talk to you about temperature and its effects on a reaction, then you're going to have this bit here. So we are going to have a delta H, which basically is the energy change. So delta is always the shorthand way of writing change, and H is all to do with enthalpy, which is energy. So what we will have is a delta H for the forward reaction. And you need to look very carefully at this. Is it positive or is it negative? If it is a negative sign, that tells us it is exothermic. If it is a positive sign, it is endothermic. If our forward reaction is exothermic, so it's got the negative sign, then that means the backwards reaction is endothermic, because it's the opposite. So, in this example, increasing the temperature is going to move it to the left, because obviously the forwards reaction is exothermic, therefore increasing the temperature moves it in the direction of the endothermic change, which means we are going to move it to the left. So just remember those couple of key facts there. Look at the sign first of all. Is it exothermic? Is it endothermic? And then the equilibrium position will move in the direction of the endothermic change when the temperature is increased. Quick reminder for us here, this is our summary, almost like a little cheat sheet if you like, just to help you remember those. Pressure towards the fewest moles of gas. Concentration away from the substance where the concentration is increasing, and temperature in the direction of the endothermic change, and we're looking for a positive energy change for endothermic. Quick reminder then of our daily formula. Work done in joules is the force in newtons times the distance in meters. For today's physics prep, we're dropping back to P2, so this is on the first physics paper, and we're going to have a little look at velocity time graphs, not to be confused with distance time graphs. And the way we avoid that confusion is we will always, as first port of call, look at this label on the y-axis. If it says distance, it's a distance time graph. If it says velocity, it's a velocity time graph. Now, when we look at the velocity time graph, we've got 4 key features we need to know. Firstly, a horizontal line. So where we've got this horizontal line, that tells us it is a constant velocity. And we can see that because when time passes, it's clearly staying at 8 meters per second in that example. If we've got a diagonal line, then we have a constant acceleration. If it's a curved line, it would be a changing acceleration. And then if you want to know what the acceleration actually is, that's just the gradient of the line. So how do we calculate the acceleration? Well, that's quite simple, because you will have a section of graph that is just a diagonal line. Now, if it's over the whole thing, then obviously we can use the whole graph. If it's for a fixed time, then obviously read the question to know what the times you are using are. In this case, it's over the whole one. So the first thing we need to do is find the change in the velocity and the change in time. So if we look at our graph, our velocity starts at 0 and it goes up to 20. So we do 20 minus 0 gives us a change of plus 20 meters per second. Do the same for the change in time. We start at 0 and it goes all the way up to 5. So 5 minus 0 gives us 5 seconds. So we've got our change in velocity and the change in time, and then hopefully we remember that acceleration is the change in velocity divided by the change in time. So all we then do is substitute it in. So we've got plus 20 divided by 5. 20 divided by 5 gives us 4 meters per second squared. And that will obviously be plus 4 meters per second because it was plus 20. And that's it. If they ask you to calculate the displacement, then what we're looking at is the area under the graph. So we're looking at the green line. Now, when we look at our green line, it's a weird shape. Now, most of us, if not all of us, will know how to calculate the area of a triangle and the area of a rectangle. So what we start off by doing is dividing our weird shape into shapes we know. So we can divide it into 2 triangles and a rectangle. Then work out the areas for each. So if we start off, we'll just number these 1, 2, 3, just so you know which bits I'm talking about. So triangle number 1 first of all. If we have a look, then in order to work out the area of a triangle, it's half the base times the height. So our base is 0 to 4, so that is 4 times the height, and we go from 0 up to 8, so 4 times 8, and then remember it's going to be half. So again, you can use a calculator, you don't have to do any of this in your heads ever, and then that is going to give us an answer of 16. So that's our first bit. Then we're going to do the same for the rectangle. So the rectangle goes from 4 to 7, so that obviously gives us 3, and then we're going to times that by its height, happens to be 8, so 3 times 8, and that gives us 24. Then we do the same for our triangle number 3, so from 7 to 10, that's going to be 3, and the height is 8, and we'll then times that by half, and that gives us 12. All we then do, add those up, so 16 plus 24 plus 12, and again use a calculator, because when you're in exam situations it's very easy to mess up on simple maths, and the answer to that is 52. So in terms of the displacement, it would be 52 meters. Hope you found today's booster useful, and don't forget to join us again tomorrow for the next one.